Test benchmarks. Which one now and in future? In this video, I'm going to show you how to choose the right benchmark for you and how to choose one that hopefully still will be around a couple of years down the road and that is maintained throughout. I'm Cyril Arthur from KTH, and this work is joint work with Adam Benali from KTH and Rudolf Ramler from the Software Competence Center Hagenberg. Now, what is a benchmark and why do we need them? A benchmark is a representative selection of problems or of examples that allow us to evaluate how well different products do when subjected to these examples. Well-known examples of benchmarks are examples for processors that evaluate how fast the processor handles a certain computational load. The idea is that somebody who wants to buy a processor can choose one that performs best under certain types of loads and hopefully is the fastest for doing everyday work. Besides CPU benchmarks, more recently GPU benchmarks for the graphical processing units have also come up with the same goal. Benchmark collections cannot be used to evaluate only products, but they can also be very valuable in our research. The idea is to have a perfectly reproducible setup for experiments that is hopefully also objective and allows us to compare realistic loads and realistic examples for different types of tools and approaches and algorithms. Now, what benchmarks are actually out there? To find benchmarks for testing in common programming languages, we first performed a keyword search and a search through the recent top conferences and journals to see what kinds of literature is out there. From that starting point, we performed a snowballing search by looking at the references in these papers and newer papers that cite the old ones. From there, we got 35 benchmark collections as a starting point. We then performed additional screening on them, based on 3 criteria. First, a benchmark has to be publicly available. If it's only available by contacting the author of the benchmark, we did not consider it, for example, because we wanted to have a benchmark that is really easily accessible and that we can be sure we can access still 2 or 3 or 10 years down the road. Second, the benchmark had to have a certain level of documentation, such as a paper or a report. And third, it had to contain defects, because we wanted to look at benchmarks for test case generation. And in testing, we don't only want coverage, but also we want to know how well a certain approach can actually find defects. After using these 3 criteria as an additional filter, we arrived at the final collection of 23 benchmarks, on which we performed our analysis. We analyzed the final set of 23 benchmarks to see what kinds of key attributes are out there and how we can compare them. Some attributes are rather obvious, like the size in terms of thousands of lines of code, how many programs they contain, and if there are known defects, and if so, how many. For all the defects, some benchmarks have a fixed version, but the majority of them might only have a defective version that is labeled as such, and maybe some other unrelated examples of correct programs. The programming language itself is of course an important attribute, as well as whether we have only sequential programs or also concurrent programs that might have concurrency issues like data races or deadlocks. Another point was the infrastructure. Not all sets of benchmarks actually have an infrastructure to compile them, because a few were designed for source code level analysis. Practically all benchmarks have a way to compile all the examples automatically though, and most of them also have a way to execute them in their default setting. Typically, it's very difficult to know what kinds of properties we should verify. Therefore, it is extremely helpful if benchmark code also contains assertions. The assertion density, the number of assertions per 1,000 lines of code, is an indicator of how well annotated the program is and how effective automated test case generation can actually find defects rather than just cover statements and branches. Another important attribute is whether we look at metadata or actual data. Metadata contains links to other archives or repositories, while actual data includes a copy of the code that we want to analyze. If a benchmark collection has only metadata, then it is only a matter of time until these links will no longer be accurate, because the source has moved or is maybe even taken down without replacement. It is therefore important in the long term to have the actual data in the benchmarks so we can be sure that we always have the code available. When we look at all the benchmark sizes, we see that we have a vast range available, from a few thousands of lines of code to almost 100 million lines of code. Now, this huge range is really hard to visualize. So let's turn to animals and their mass to get an idea of how much of a size difference we have here. The smallest benchmarks have a few thousands of lines of code, which is similar to a cat. Here, 1 gram means 1 line of code, and 1 kilogram, 1,000 lines of code. If we move then to a larger range, we get benchmarks the size of a cheetah, between 10,000 and 100 lines of code, a cheetah being 50 kilograms, somewhere in the middle. One order of magnitude higher is a bison with about 500 kilograms, and the really large benchmarks are moving towards the size of an elephant, which can be 5,000 kilograms or 5 million lines of code. And the very largest benchmarks are the size of a large whale. We have 2 examples that are that huge. One is about 50 million lines of code, and the other one is about 100 million lines of code. However, these are not just huge programs. In that case, they include all the expanded include files in the code. So the actual example code is much smaller, but the include files are there, so we do not depend on the locally installed include files and really have a fully reproducible range of code that we can use. So we don't suddenly need to find an old version of an include file that may no longer be so easily accessible. When we look at the programming languages, we see that C and Java dominate. That's not surprising because those are 2 of the most popular programming languages out there. For all the other mainstream programming languages, we can usually find a benchmark set too. However, there is a problem if we want to find a benchmark for the latest version of a programming language. The benchmark sets usually have been around for a while or are somewhat recent, but they do not reflect the latest version of the programming languages. And for languages like Java or Python that are still evolving quite fast, this is a real problem. In Java, we get a new release every year, more or less, and many new releases add new language features and even take some library functions away. This means that an environment now is not compatible with an environment from 3 years ago or 3 years in the future. If you have a tool and want to evaluate it on examples, these examples had better work with the programming language you use. So a benchmark that worked 5 years ago and no longer works now is not very helpful. And here we see the need for updating these benchmark collections on a regular basis. Finally, we miss out on new language features, like for example, lambda expressions in Java that have been around for a couple of years. They are not very well reflected in benchmark collections. So the tools will be biased towards older features if the benchmark collections are not updated. Licensing is maybe a topic that doesn't interest programmers a lot, but it is actually very important. Without a license, the Berne Convention for copyright applies. So while you can see the benchmark on the web browser, you're actually not necessarily allowed to download, compile, and use it, much less modify and perhaps redistribute it. Only a license gives you the right to do what you want to do. And therefore, a benchmark should really come with an open source or at least a research-friendly license that makes it clear the benchmark is meant to be used in many ways and that the author doesn't impose restrictions on them. It's important that if you collect programs from other sources, that you always track the authorship and the license, and you include the license for all the examples. Unfortunately, almost a quarter of the benchmarks that we surveyed didn't have a license, which means it's not sure if it's actually legally safe to use them. Most benchmarks that we saw have been developed in the last 7 years. A few have been around for longer than that. And if you look at the lifetime of a benchmark, the duration for which they have really been maintained and for which modifications have been made to the examples themselves, we see that most benchmarks are very short-lived. It's as if they are set in stone and never updated again. And their lifespan, in a sense, is only 1 year. Of course, we can still access them, but they have not been updated since their creation, or at least a year of their creation. And this is a problem. If we look at the lifespan of benchmarks compared to the lifespan of animals, we see that most benchmarks have the lifetime of a dragonfly, which is up to a year. A few benchmarks live slightly longer, which is about the lifetime of a mouse, a few years, or even the lifetime of a hare, 5 to 7 years. But only 3 benchmarks in our set of collections that we analyzed had a lifetime of 10 years or more, which is the lifetime of a reindeer shown here. And we as a community should really try to produce more sustained benchmark collections. So let's make more reindeer-like benchmark sets rather than dragonflies. This is easier said than done. It's not only a problem of the research funding, but also an issue of how the benchmark is set up. And we identified 3 key success factors in this. One is that the benchmark is hosted openly. There is no complex registration procedure required to access it. Ideally, it's on a Git repository, so we even have a well-defined mechanism for third-party contributions through a pull request. Second is that the provenance, the license and authorship of the examples is clearly maintained. The license shown here is the MIT license, but any flexible and permissive open source license is appropriate here. And in addition to that, we need to make sure that we remember who wrote which benchmark. And third and finally, the metadata of the benchmark should be in a uniform and machine-readable format, so we can really easily compare and analyze benchmark collections, and we do not have to read through license files by hand. One example that fulfills all these points is the SV benchmark collection, which has complete licensing, which is openly accessible and allows third-party contributions, and even has all the information about licenses in a machine-readable format. To summarize, benchmarks are an important research resource. We need them to assess and compare our test algorithms and tools. However, it's not enough to just put the benchmark out there. It has to be made available with a license. Just publishing code doesn't make it open source if we forget to include a license. Finally, the duration for which a benchmark is maintained is a huge issue. Let's become more sustainable as a community and try to put in more long-term effort. And let's also honor this by giving weight to publications that update and maintain benchmark collections rather than just producing a new one. Thank you for your attention.